You take it. I was doing that count. All right, so make sure you all have your calculators. We're going to finish up with number 3. And then there's still a little bit more calculator work that we haven't quite seen, and that is with graphing and being able to interpret graphing. So we'll spend a good chunk of our time doing that and kind of walking you through it. But we should be able to get through most of everything today. And if not, then we still have half periods tomorrow and Thursday to get ready. And also help sessions tomorrow, Thursday, and Friday morning. I'll send out a reminder this afternoon. Okay, so just to recap, we talked about how we're able to, from the starting definition, we're able to build our derivative and second derivative simply by taking the derivative actions on that right side. So we know the derivative of an integral is really second theorem, and second theorem is going to allow us to get the operation or these two operations to cancel each other out, and we're basically down to f of x. And g double prime is f prime, so there's that staggered relationship. G is the area under the f, g prime is the order pair of the f, and g double prime is the slope or the derivative of f. So at g of 0, we just follow what the rule says, right? So we never have to guess what to do in terms of the bounds. We just plug in wherever the x is located. In this case, from -3 to 0, we see that the area, all this is above the x-axis, and we just have to add the two areas together, keep the value positive. G prime of 0 is the y value, is f of 0. F of 0 is asking for the y value of the f graph. And g double prime of -1 is asking for f prime of -1. F prime of -1 is basically saying the derivative or the slope of this line segment. The slope of this line segment, I just do rise over run, down 1/3, -1/3. Okay, so continuing on, part C. Part C says find all values of x in the open interval -5, 4, in which g attains a relative maximum. So I want us to kind of recap review some of the things that we learned last semester. So we know that this is the f graph, but we know this is also the g prime graph. Right? So this is the g prime graph. That means this is the derivative graph of g. If this is the derivative graph of g, if you remember from last semester, that means that this y-axis no longer represents, or doesn't represent the y value of the g function. It represents the slope value of the g function. So to help remind us of that, I like to kind of mark up the sides of my graph here. Anything above the x-axis represents where my g graph will experience what? Positive slope. So I use that arrow to indicate that, these are all places of, some of these may be rising and falling, but these all represent different variations of positive slope. Okay. Here, anything below the x-axis was representing negative slope. Anything on the x-axis is slope 0. Okay, so let's create our slope sine line based off of this. So here's part C. So here's my G prime sine line. All right, so we know that we're starting at -5, we're ending at 4. Okay, where are my critical points? Remember, these are, we don't want to look at the peaks and valleys, right? Peaks and valleys represents the points of inflection of the original graph. This is the derivative graph here. This is not the original graph. So we're looking for slope zeros from the derivative standpoint. Good. So slope 0 is the x-axis, right? This is the derivative graph now. So -4. Okay, where else?
+1, +3.
Okay. Okay, so we want to match the arrows in terms of how the graph is moving. So between -5 and -4, what's happening with our graph here?
Increasing.
Right, but look at the arrows here. The arrows is giving us an indication what's really happening of the original graph. Decreasing. The increasing indicates that the negative slope is becoming less steep, but these are all considered still quote unquote negative slopes. Right, so -2, -1.1, -2, -1.3, -0.9. Those are all negative slopes, but we want to indicate what the slope is doing here, negative slope. That's going down. Between -4 and 1, look at where the graph is located. Don't look at the rise and fall of the graph. Look at where it's located. Is it above or below the x-axis? Yeah, it's above, so we want to indicate that as a positive slope. Between 1 and 3, 1 and 3 is still increasing, still above the x-axis. Look at the arrows here. Between 3 and 4, not because it's falling, not because it's decreasing, but because it's below the x-axis, right? Below the x-axis, remember, this is not the shape of the G graph. This is just the slope values of the G graph. Okay, so part C is asking, find the values at which G attains a relative maximum. So where do we expect relative maximum to exist?
In between -4 and 1, in between.
Okay, where do you see relative max? At 3, because my slope is rising followed by falling. So relative max is a hill of the graph, right? So the hill of the graph we can expect to show up at 3. So we can say relative max at because G prime is the G prime graph. G prime changes from positive to negative. Okay, part D. Part D says, find the absolute minimum value. You guys remember from first semester, what theorem do we involve if we want to find absolute minimum? Yeah, extreme value theorem. Okay, so EVT. You guys remember from EVT, what are the candidates that we want to involve if we want to find absolute minimum or absolute max? Yeah, that's condition. Condition is continuous, but what are our candidates? Where do we look for absolute, or what do we need to consider if we want to find absolute max or absolute minimum?
We're changing signs.
Endpoints and endpoints and critical points. In this case, we don't have to consider relative max because there's no chance that a relative max, a hill of a graph, can never be the lowest point on the graph. So we only have to consider test endpoints and then test your relative min, right? And we're trying to do this without, right? We don't have the graph, the actual graph in front of us, but what we can use is we can use a slope sine line to help us identify candidates, and then from the candidates we can figure out, if we can find a way to get to the y value. Okay. So We definitely have to test what? What are the endpoints? Yeah, -5 and 4. We'll plug this into the g of x function, right? We're trying to find the absolute minimum value on the g graph. And then we have to test relative minimum. So we also want to test what? -4, right? You see the arrows are indicating there's relative min here. There's nothing at 1, and there's a relative max at 3. So we don't consider 1 and 3. I mean, we can test it, but we know that they will never end up being the lowest y value. Okay, so we have 3 candidates, right? -5 and 4 as endpoints. And then from the relative minimum, we'll test x equals -4. All right, so we're going to go through one by one here. So let's start from the left side. We're going to find g of -5. And to find g of -5, we just have to follow whatever this definition says. Okay. Are we good so far? Okay. Using the definition, we'll use the graph and gather what that y value is going to be. Okay. No need to guess what's going to happen here. Just copy whatever the rule tells us. The rule tells us to go from -3 to -5. So we're going to be involving area components under the F graph. Now we want to read the graph, right? What will make this easier to read? What do you notice about the way that we set this up? We're kind of forced into setting this up, right? We had to put the X up here. What do you notice about the setup? Yeah, the bounds are out of order. It's easier if we can read the graph from left to right. So if I want to read the graph from left to right, that means if I read from left to right, that means below is negative, above is positive. I don't have to think backwards in terms of, oh, now I got to adjust above is negative, below is positive. It just feels more difficult that way. So I'm always going to adjust the bounds if I'm forced to read the graph, right? So if I adjust the bounds, what can I do to still make it the same thing as what I'm starting with? Yeah, pull the negative outside. Okay, so we're going to figure out what this value is, and then in the end, we'll just change the sign of that value. Okay, that way we can ensure that we haven't changed the overall what we're looking for. Okay, so let's just focus on between -5 and -3. Between -5 and -3 here. Right. What do you notice if I were to add up these two regions together?
Make a square.
All right, so we have a triangle here, 1/2 base times height. That will be a negative value. This is also a triangle, 1/2 base times height.
Okay.
So it cancel out to be what? 0. Okay, so that's just 0. I mean, we can find the area here. I mean, that's fine. The area here would be 1 times 2, 1/2 base times height, so -1. This is a +1 here. Okay. For future reference, we may need it. Okay, but we know it's going to end up being 0. -0 is still 0, so okay, so we're good there. We have an order pair for g of -5. Ultimately, when we find all of our candidates, we'll just compare the y values, and whatever has the lowest y value is your absolute min. Okay, good so far. All right, what can we test next? Yeah, we can test 4 or -4. I'm gonna do this. I'm gonna go from left to right. That way, we can kind of just accumulate, but it's fine. If you want to test them out of order, that's no big deal. It's just, yeah, I'm just gonna go from left to right. But it doesn't matter which order you test these points. Okay, so let's follow what the rule says. Where does the -4 go in our integral? Our definition tells us to start up here, right? So if it's out of order, we can adjust later, but we always have to do whatever the definition tells us to begin with. Okay. Any adjustment needed? Yeah, let's flip the bound. Let's change the order of the bounds because the -4 is the lower number, right? We want the lower number below, and then just pull a negative out in front. Okay, so I'm going to figure out what this piece is, and then I will change the sign after I figure out that number. Okay, so from integral from -4 to -3, what's that going to be? What shape do you see there? Triangle, right? 1/2 base times height, that's equal to 1, but then we can change it to a what? -1. Okay, we have one more to go. G of 4. Okay, go back to your definition. G of 4, we plug the upper bound. How about this one? Do we need to change anything? This one's good, right? This one is in the order that we want from lower to upper. So we just have to add up all these regions that we see here from -3 all the way to 4. Now, this part is okay. This isn't too bad. These are true triangles here. 1/2 base times height, 1/2, 1 times 1. This will be -1/2. And this is going to be +1/2. Now, these little regions here are not geometric shape by themselves, but we can get to those areas using geometric shapes. How can we get to these two little regions here? Good. Good. Rectangle minus a semicircle, right? These on their own is not geometric shape, but we can combine geometric or use geometric shapes to get to that area region. Okay, so rectangle minus semicircle. Okay. So I'm gonna do the work here so I don't have to spend all the space here. So it's a rectangle minus a semicircle. Okay, so rectangle is length times width or base times height. Semicircle is 1/2 pi r squared. Okay, so what's the area of this rectangle here? Like 2, right? 2 times 1 is 2. And then what's the radius of the semicircle? 1. Okay. It's just this distance, right? 1. Okay, so 1/2 pi times 1. So 2 minus pi over 2. Right, so this whole region here is 2 minus pi over 2. Now, you'll get to use your calculator, but technically this is a non-calculator question. I just want to show you how we can do this without a calculator, especially from AP exam perspective. Whenever you see pi, we can just treat it like what? Just for an easy estimation. Yeah, 3.4, but even easier, let's just think of pi as what? Not a variable. It's 3, right? That way, in terms of when you're making your calculations, you don't have to do a whole lot of messy math, right? Just think of that as 3. So it's really 2 minus 1.5. So this is really estimated to be what? 0.5, right? So it's around 0.5, just for you to, enough for you to know which was higher and lower, right? So, okay, so I'm going to add up all the areas that we see here from -3 all the way to 4. So I have 4.5, right? 4.5 plus 0.5. Okay, I know this is just estimation, but enough. Now, on the test, you can use your calculator to double check everything, but I just want to show you what it would be like if you were to do this without a calculator. Okay, 4.5 plus 0.5, and then what? What's going to happen here? Cancel out, right? So I can do plus 0.5 minus 0.5, but ultimately it's just going to cancel out. Okay, so 4.5 plus 0.5, that's around what? Around 5. Okay. Enough for us to, we don't have to be completely accurate, right? We just need to have enough information to compare and know which one is highest and which is lowest. Or sorry, in this case, just what's lowest. So what can we say? What's our absolute minimum? Yeah, but what can we say is the answer though? What's the absolute minimum value? Good, that's the y value we're looking for. Okay, so we can say our answer. We know that we tested all of our valid candidates, and of these 3, whatever's the lowest must be the lowest overall in our region. So we can say absolute minimum value is -1. This is all you need to say, but if you want to say the x value, you can say it later at x equals -4. Don't give order pair, give the y value. And if you really want to say the x value, say it after, but don't say it at the same time. Your absolute minimum value is asking that word there, value means y value.
3 points in that first place like this.
Right. So we look at our sign line and we use that to help us figure that out. So yeah, word changes signs and wherever there's a relative minimum, because this is only asking for absolute minimum. We don't have to look, we don't, anywhere there's, you see how there's a relative max at 3 because the graph rises and falls. There's no need to test 3 because a relative max can never be an absolute minimum. So we only test endpoints and critical points. In this case, the critical point is the relative minimum.
Also, for the relative minimum, then that's like blends in between positive and negative.
Because the graph is falling followed by rising. So if the graph is a relative minimum, that relative minimum could end up being the lowest point on the overall graph. Okay, last part, part E. Find all the values in which the graph has a point of inflection. So remember, this is the derivative graph here. Okay. How do we find points of inflection if we're looking at the derivative graph? Peaks and valleys, right? The highest and lowest points of your graph. So where can we say points of inflection are if this is a derivative graph? -3 is 1. Okay, where else? 0 is not quite. I know there's a sharp turn there, but it's not a peak or a valley, right? It's falling and it's continuing to fall. So 0 is not a relative max or relative min. Where else? Yeah, 1. 1 is a relative minimum. So we want to that's going to be point inflection. And where else? And 2. Okay, so we have -3, 1, 2. Of your derivative graph, right? Of your derivative graph.
But you don't count the endpoints.
That's right. The endpoints are not going to be a relative max or relative min. That's right. Okay, I want to create a sign line here just so I can convince myself. I don't have to go through. I didn't have to go through all this, but it's nice just to have. If the question was asking about concave up, concave down, we can provide that as well. But I'm going to have the endpoints here: -5 for, we said what, -3, 1, and 2. Okay, this is my second derivative graph here. It's not needed for this problem, but it may be needed for a future problem. So I just want to fill this in here. How do we find concavity if we're looking at the derivative graph? Look at the what? Not the arrows here. Now we can look at the behavior of the graph, right? Wherever there's a positive slope on the G prime graph indicates where the G graph is going to experience what? Concave up. Yep. So positive slope means concave up. Negative slope means concave down, right? Don't look at the curvature, right? This is not the original graph, so we're just basing it off the slope. But it's going to keep alternating, right? Positive slope, negative slope. Okay, so points of inflection are -3, 1, and 2. We can just say because G double prime changes signs. Okay, I want us to get comfortable with the graphing features in our calculator. So if you guys can turn to page 6, we'll spend the rest of our time today going over that. That's what we need most need most time with here. The graphing. Yeah, so that's the last one. Page 6 will be the last one. We saw some of it in terms of the particle motion, but we haven't delved into the graphing yet. Okay, page 6. All right, so you need your calculator here. All right, so everyone has graphing calculator. If you need one, you can grab one of my older ones up here. So it says an object moves along a horizontal line. V of t equals 4 sine of t squared minus 2t plus 2, measured in meters per second from 0 to 4. Hint, we're going to set the windows to these x and y values. So go to y equals. Make sure, again, you're in radian mode. Okay, we'll type in 4 sine of t squared minus 2t. Again, always use variable what in your calculator? X, yeah. We're always in radian mode. We're never in degree mode. On the AP exam, oh yeah, sorry. You're going to just go to mode, click on mode, and then scroll down and make sure radian is highlighted and not degree.
X setting as T in the calculator.
Right. Never use any variable except X in your calculator. Right. Oh, sorry. +2. Okay. I want to show you 2 ways to get the graph to show the portion that you want to see. But for right now, let's just follow whatever they say. We're going to adjust the windows here. So go to Windows. So window is this button here next to y equals. And these will set the how far left and how far right you want the graph to see, and then how far up and how far down you want the graph to see. So right now, it's showing you as far left as -10 on the x-axis, as far right as +10 on the x-axis, as far down as -10 on the y-axis, and as far up as +10 on the y-axis. These are the only 4 numbers you're ever going to play with. Don't look at the scale. Don't look at anything else. So here, we're going to set from -1 to 5. So -1 for our x. So we only need to go as far left as -1. We only need to go as far up as a +5. Y value, we want to go as far down as -6 and as far up as 6. Next up, you're going to hit graph. Right. So this is the velocity graph here. Right. It's asking, okay, is everybody okay here?
I got an invalid dimension.
Okay. Make sure that you are doing your min is lower than your max. If it's not, then it's going to start complaining. So make sure your min is -1, your max is 5, your minimum is -6, and your max is 5. Sorry,
Is it still doing that?
still doing that. Okay. Oh, let me just show something here. For some reason, I don't know why calculators do this, but sometimes do you see how above there's that plot 1 highlighted? Just if your plot is highlighted or plot 1, plot 2 is highlighted, just go up to that plot, unhighlight it, and just make sure that is not interfering with your graph.
It's clear.
Now just hit enter. Hit enter, and then you can try it. Go back up, highlight it, unhighlight using the enter button.
And that's like why it shows it as.
Yeah, so just always make sure it's unhighlighted. So yeah, so that's a good point. If you ever get that dimension error, make sure that your that above your y equals, you don't have any highlighted plots, 1, 2, or 3. Okay, all right, go to graph. Now, this is the velocity graph, okay? So part A, it says, find the time when the object is motionless. So if we want to find out when the object is motionless, we're basically looking to see wherever this velocity graph hits what? It's what? It's the x-axis, right? So we have to basically figure out where is the decimal where the graph touches the x-axis. Now, we can trace, but the trace feature is not going to be as accurate as we would like, okay? It's getting close, but it's not quite getting where we would like. So I want to show you how we can get enough accuracy for AP exam, to be satisfied. So what you're going to do, I'm going to write down these instructions here, but we're going to do second trace, and we're going to select that 0 feature. Okay, second trace 0 will allow us to get to that 0 or that x-intercept. Okay, I'm going to write these down. Let's see my instructions. Okay, so defined x-intercepts on the graph. Okay, so first you're going to go to second trace, select 0. And the second, okay, so go ahead and hit enter when you or at 2, or you can hit 2. Now you're going to scroll to the first place that you're going to target with your x-intercept, right? So let's say my graph looked like this, right? Okay. I want to target that x-intercept. You're not going to do the guessing, okay? Make the calculator do the guessing for you. So it has 3 questions for you. It says it's going to ask you for left bound. Okay. Now, when it says left bound, what you're going to do is you're going to scroll to a point that is to the left of your target point. So it doesn't matter where, just as long as it's relatively close. And then once you get to that point, you're going to hit enter. Okay. And then the calculator is going to know, okay, when you do that, the calculator knows, okay, you want me to start looking for the x-intercept from this point, okay? Don't put your calculator directly on the x-axis. Then the calculator is going to get confused. It doesn't know where to start and where to end. You're going to give it a range of values, and then it's going to go looking for the x-intercept, okay? Don't look for it on your own. If you do, the calculator is not going to be able to do the work for you. Okay, next up, if you hit enter at a point to the left of the x-intercept, it's going to ask you another question. It's going to say right bound. And guess where we're going to go with our cursor? Okay, on the other side. We're going to go to the other side of the x-intercept. Okay, it doesn't matter where, as long as it's relatively close. I'll use a different color here. And then you're going to hit enter here. Okay, everybody okay so far? Now, it's going to say guess as your 4th question. Do not move the cursor, just hit enter. Okay. Basically, when it says guess, the calculator just wants to know, okay, are you ready for me to look for the x-intercept for you? Okay, don't try to move the cursor, just hit enter a 3rd time. So you hit enter 3 times. Once with the left bound, once with the right bound, and once when it says guess. And when it says guess, hit enter again. It's going to find that x-intercept for you. 2.46. Now this is looking strange here. It's -8 times 10 to the -13. It's basically saying what? That's a really, really small number, close enough for us to say that's equal to what? 0. Right? So don't worry about, wait, what does that number mean? For some reason, they're not rounding to 0. It's close enough for us to say it's 0. So, and it also says the word 0 here as well. So my x-intercept is 2.463.
Did you ever take a calculator?
I'm sorry?
You demonstrate on like the calculator, like which points are you supposed to put the enter on?
Right. It doesn't matter as long as you pick a point to the left of the x-intercept, and then pick a point to the right of the x-intercept, and hit enter again, and then it's going to find that x-intercept.
So it doesn't really matter. You just
hit enter. Yeah. And then scroll to the other side. Hit enter again. Hit enter 3rd time.
Let's go find that. Okay, thank you.
Anybody else have questions? Now, just for future purposes, the same thing applies if the problem, let's say you want to find a relative max or a relative min on a graph, for instance. It's not going to be in this case, but if you were, you'll do second trace, and let's say you want to find a maximum, then it's the same idea. If I want to find a maximum, I'll pick a point to the left of the max, pick a point to the right of the max, hit enter a third time when it asks for guess, and it's going to find that intersection or that max for you. All right. So we'll do this a couple of times because we need to find all the x-intercepts between between 0 and 4. Okay, because this is our bound. Okay. So we'll do this 3 times because we have 3 x-intercepts that we can look for, right? There's 1, 2, and there's a third one that is slightly to the left of 4. Okay, so we'll do that 3 times. And when we do that, after we do that, we can go ahead and write out those. We can create our velocity sign line just so that we can use it for future purposes. So the first one that we found was 2.463. And then you will repeat the process again for the next 2. The next one is 3.299. And the last one is 3.903. Okay, we're going to create our velocity sign line here. We just want to indicate if it's positive or negative velocity. Anything above the x-axis indicates positive velocity. Anything below is negative velocity. So up to the 2.463, where's the graph? Above or below? Above. So we're just going to indicate that it's a positive velocity. Just for future purposes, it's nice to fill out our sign line as much as possible so that we can just have this data in front of us. I'm sorry?
We found the x-intercept that's like past.
No, because our interval is from 0 to 4. Right. Okay, from 2.463 to 3.299, where is our velocity? Below, so negative. From 3.99 to 3.903, it's positive. And then to the right of it's slightly below. So we have this keeps alternating signs here.
So I don't know if you already remember. How do you find the over 2 points in 3.299 and 3.9?
Oh, so we repeat the same process. So if I do second trace 0. Yeah, that's right. So I'll pick a point to the left of my target, pick a point to the right of my target, hit enter again. Yeah, so the same process they did the first time, but for the other 2 points, for the other 2 x-intercepts. And again, these numbers look strange, but just know that it's just basically 0. All right, so what can we say then? At what time is t is the object motionless? These 3 times, right? Okay, because velocity is equal to 0. And then that also relates to part B. When does the object change direction? We can also know that object change direction at also these points because it's moving right, it stops, moves left, stops, moves right, stops, moves left. So these 3 critical points ends up giving us the answers for both A and B. By the way, I do have the keys attached to your packet further on in the packet, so just to let you know. Okay, let me move on here. Next up, it says find the velocity of the object at t equals 3 seconds. So I can just do what? Plug 3 into the into the equation, right? So we can do this by hand, or we could do what we did yesterday with the vars, y vars. We already have our velocity stored under y1. So if you do second mode, go back to your home screen, and then do alpha trace y1. Or if you don't have the newer calculator, you can do vars, y vars function y1. So, and then plug in 3. But you can also do it by hand, either way.
You put in the white one?
We'll do y1, 3. It's asking for the velocity at 3 seconds. Okay, units of measure is meters per second. Okay, I have the velocity function. How can I find the acceleration at 3? Yeah, the end derivative, right? So math 8. Alpha trace. And if you're using an older calculator, your end derivative is going to be y, comma, x, comma, and then in this case 3. What's our unit of measure going to be? Yeah, meters per second or meters per second squared. Oh, right. So up there, it'll be y, comma, x, comma, 3. Let me see. Yeah, I'll leave this up on the board for the test. Just, the syntax takes some time to get used to. Okay, part E, is the object speed increasing or decreasing at t equals 3 seconds? Because, yeah, so speed increasing is talking about comparing signs, right? So velocity and acceleration have different signs. If they have different signs, that means my object is slowing down. Speed is decreasing. Displacement. Displacement is just the integral. Okay. Basically, how much forward or back or how much progress did this object make in that time interval? So we can do math 9 from 0 to 4 of our velocity function. Okay. And if you're using an older calculator, you'll do f integral. We'll type the function, comma, x, comma, lower bound, comma, upper bound. Which one? Yeah, so increasing, decreasing speed depends on comparing velocity and acceleration. If these both have the same signs, that means speed is increasing. So it could be both positive or both negative. That would mean speed increasing. But if one is negative and the other is positive, it doesn't matter which is which, my speed is going to be decreasing. Decreasing. Okay, we'll try part F here. So math 9. 0 to 4. Alpha trace y1 dx. Part G, total distance looks a lot like displacement, just with what? With absolute value, right? So absolute value needs to be around the velocity function. So with an older calculator, it'll look like this. It'll be Fn integral. Again, to get to absolute value, you're going to do math number ABS. Make sure you do that after you do your integral notation. Now, even though this is what you're entering in, especially with your older calculator, you're not going to write this down. You're going to write it in this acceptable notation here. This is just calculator notation, just for your, just so you know what your screen will look like. Don't worry about H and I. We can skip those. Yeah, so you're going to do, you're going to do math 9. You'll just go from 0 to 4. And then you'll get that absolute value feature to show up. So you're going to do math number ABS. So math number ABS. Put in that y1 inside the absolute value and then dx. It may take a few seconds here, but it'll eventually get to that 12.178.
Rendering H and I.
Right, skip H and I. Okay, for part J, it says, given x of 0 equals 2, find x of 4. This goes back to that formula that we talked about. Anytime we're looking for a final position, it's equal to the initial position plus displacement. So in other words, x of b is equal to x of a plus the depth integral from a to b of b of t. So in this case, what's my b value? I'm looking for x of what? X of 4. Okay. Where am I starting at? 0. Is it because we always start at 0 or because why? Yeah, because it says it, right? That's whatever they give us is what we have to do to use. Plus the integral from a to b of b of t dt. So we know x of 0 is 2. We know our displacement is, you can type it in again, but we already have it from part F. I'm sorry? Yeah. Meters. Yes. Okay, we didn't quite get to average velocity, which is average value theorem, but we got through what I want to get through today. So tomorrow we'll start our next unit. I'll get through the notes, and then we'll spend the second half just continuing to review. All right, come get your phones. Test is on Friday. House sessions tomorrow, Thursday, and Friday.
President from K&L.
Yeah.
Is this all just review for like?
You can take it next Monday. Is that okay?
Monday morning.
That works.
You?
Oh, yeah. Thanks.
Sorry.
Sadie, what'd you say?
Like this is all just for the review and then we'll get a new package.
But a new packet, we're just starting ahead with new notes. It's not going to be on the test. I just wanted to.
So we just need to know 3 different things for that.
Right. It'll be particle motion like this one. It'll be a derivative graph like the one we just did. And like yesterday, table of values, 3-month sums. That's fine. Anytime Monday works. Yeah.
things. Are there anything for the non-calculators? Can you come back on this mess? Or they're being statements?
Just know your area for rectangles and trapezoids.
Okay.
That's it. Yeah.
Will it be like increasing?
It may take a little bit. I'm gonna be able to make some grading this weekend, but probably won't be until like middle of next week, I think.
Who you rooting for this?
I think I'm with you, San Fran. But I do want to be a close game. I think it's more fun to watch a game that's close.
I just don't want Chiefs to win.
I know.